Hi everyone. In the last video, we focused on the greatest common factor. In this video, we're going to focus on a related concept, the least common multiple. As with the last video, we'll start out with some discussion of the least common multiple, or LCM, and then work several examples. The least common multiple is a multiple, and what does that mean? Let me get my pen going. For a number n, so for any number n, a multiple of n is a number of the form n times k, where k is a whole number. Numbers of that form are multiples of n. So for example, if the number in question, if n is 5, then multiples of 5 are 5 times 1, which equals 5. 5 times 2, which equals 10. 5 times 3 equals 15, and so forth. Note, obviously, there are an infinite number of multiples of 5. The LCM, the least common multiple, of two numbers, which is written LCM of A times B, has two properties. First of all, the LCM is a multiple of both numbers. Multiple is the M part. Both numbers means it's common to both numbers. So it's a common multiple. Those are the C and the M in the LCM. The L part means it's the least. In other words, it's the smallest number that is a multiple of both A and B. So let's focus on a couple strategies for finding the LCM. Strategy 1 is kind of grunted out, if you will, is just make a list. Make a list of the multiples of both numbers. Now, obviously, there's an infinite number, but there is a limit to how far you're going to need to go in finding the multiples. So the LCM of 24 and 30. Start out by making a list of the multiples of 24. So 24 times 1 is 24, 24 times 2 is 48, and so forth. 72, 96, 120, 144. Those are all multiples of 24, and we could keep going. Multiples of 30 are 30, 60, 90, 120, and so forth. What you then do is identify the smallest number that's on both lists. So there is no 24. 24 is on 24 but not on 30. 60 is on 30 but not on 24. If we keep going, it turns out the first number that appears on both lists is 120. So that implies that the LCM of 24 and 30 is 120. As with the strategy for the GCF, the list strategy, this strategy works, but is often not very efficient, especially with larger numbers. And so that's the reason for the second strategy, which uses prime factorization. For prime factorization, what you want to start off with is finding the prime factorization of each number. In other words, identify the prime numbers that are factors of each number, and then examine identify the prime numbers that are contained in either factorization. It doesn't have to be common to both, it has to be present. And then identify the greatest exponent for each of these prime numbers. So we already know that the LCM of 24 and 120 is, or 24 and 30 rather, is 120. Let's confirm that with the prime factorization method. The prime factorization of 24 and 30 is, or 24, it's 2 to the third times 3. And remember, you have to write that exponent. 3 is 3 to the first. For 30, it's 2 times 3 times 5. So the first step is this: identify all prime factors that are in either of these two numbers. So 24 has the 2 and the 3. 30 has a 2 and a 3, but also has a 5. So the numbers that are in either, the prime factors are in either of these two numbers, are 2 and 3 and 5. And then what you do is identify the greatest exponent that is included in both numbers. So for the 2, you've got 2 to the third and 2 to the first. As a multiple, it has to contain all of 24. It has to contain all of 30. So to contain all of 24, we need at least 3 2's. So you identify the greatest exponent of the two exponents. So it'd be 3. For 3, you've got 3 to the first and 3 to the first. The largest of those two exponents is 1. For 5, you've got 5 to the first. There is no 5 in 24, but remember, it has to be in either one, 5 to the first. So 2 to the third, which is 8, times 3 times 5, also equals 120. And we've confirmed that using prime factorization that 120 is the LCM. Okay, let's work a few examples. And again, I think using the larger numbers allows you to see, hopefully, the sort of the advantages of the prime factorization method. For 240 and 600, again, you probably would not want to list out factors. You could. They might not take too long. But for 240, you've got the factors of 2 to the fourth, 3 to the first, and 5. For 600, it's 2 to the third, 3 to the first, and 5 squared. So the first step is identify the prime factors in either number. They each have a 2. There's a 3 in each of them. There's a 5 in each of them. And those are the only prime factors in the two numbers. Then I identify the greatest of the exponents. 240 is 2 to the fourth. 600 is 2 to the third, so we include the greatest exponent, 2 to the fourth. For 3, the exponents are both 1, so we include that 1, 3. For 5, the exponents are 5 to the first and 5 squared. 5 to the first and 5 squared is 5 squared. Let's see if I can figure this out. 2 to the fourth is 16. 16 times 3 is 48. 48 times 25, whatever that turns out to be, is going to be my LCM of 240 and 600. Note that you don't even need to know the numbers as long as you have the prime factorizations. So in our second example, we've got number A, we'll call that number 1, is 2 to the third, 3 to the third, 5 squared, 11 to the sixth. Just a large number that's popped into my head. For number 2, you've got this prime factorization. So the first step is identify the prime factors in either number. Well, there is a 2. There is a 3. They don't each have to have it. At least one has to have it. A has a 5, so we'll include 5 in our LCM. B has a 7, so we'll include 7 in our LCM, and then each have an 11. So this is probably going to be a fairly large LCM. Okay, then identify the greatest exponent. For 2, you've got 2 cubed and 2 to the sixth. The greatest of those exponents is 2 to the sixth. For 3, you've got 3 cubed and 3 to the first. So that's 3 cubed. For 5, it's only in number 1. So that is 5 squared has to be included. For 7, you've got 7 cubed. That's the greatest exponent of the 7's. And lastly, for 11, you've got 11 to the 6th, 11 cubed, so that's 11 to the 6th. That would be a large number. As we do with the GCF, you can also use this approach to examine the LCM of more than two numbers. So suppose I'd like to find the LCM of 1680, 600, and 720. Find the prime factorizations first. 1680, for example, is 2 to the fourth times 3 times 5 times 7. I've got the prime factorizations for 600 and for 720. Find all three in this case. Then go through and list the prime factors in either of the three numbers. So there is a 2. They each have a 2. They each have a 3. They each have a 5. Remember, being common isn't important, just that it exists, just that the factor exists in one of them. So 7 is a prime factor of 1680, so it has to be included in our list, even though it's not in the others. then include the greatest of the exponents. So on the 2, it's 2 to the 4th, 2 to the 3rd, and 2 to the 4th. So we include 2 to the 4th, the largest exponent. For 3, it's 1, 1, and 2 are the exponents, so 3 squared. For 5, it's 1, 2, and 1, so 5 squared. For 7, it's only included in 1680, and it's to the power of 1. So that is my LCM of 1680, 600, and 720. Again, a rather large number. Lastly, again, you don't even need numbers. You can just use these in letters. I've got two numbers described by their prime factorizations for number 1 and number 2. Okay, identify the prime factors. There is an A. B is included in number 1, not in number 2. That's okay. C is included in both of them. D is included in number 2, but not in number 1. And lastly, E is included in both of them. Again, a prime factor in either of the numbers. If it's in either of the numbers, it goes on our list. Then identify the greatest exponent. For A, I've got A cubed and A to the 6th. So that's A to the 6th. For B, it's only in number 1, so it's B cubed. For C, I've got C squared and C to the 1st, so C squared. For D, it is D to the 3rd. It's only in number 2. And for E, it would be E to the 6th and E cubed. So that is E to the 6th. So the LCM of these two numbers, number 1 and number 2, would be A to the 6th, B cubed, C squared, times D cubed, times E to the 6th.